quite literally. I mean, it's a great cliche when people say he needs no introduction, but this is not the case where that is true. And it is a real delight to me to welcome my friend and colleague, Richard Dawkins.
Well, thank you very much. Are these microphones working? So, Darwin's 5 bridges. Was Charles Darwin the most revolutionary scientist ever? If by revolutionary we mean the scientist whose discovery initiated the most seismic overturning of pre-existing science, then the honour would be contested by some of the great physicists, Newton, Einstein, the architects of quantum theory. And indeed, those same physicists might well have outclassed Darwin in sheer intellectual firepower. But Darwin probably did revolutionise the worldview of people outside science more comprehensively than any other scientist. I think he has a good claim to be the most seditious scientist. Before Darwin, it took a philosopher of the calibre of David Hume to rumble the illogic of, if a thing looks designed, it must have been designed. Even Hume, although he could see that it was a bad argument to say that because something looks designed, it must be designed, he couldn't think of a good alternative. That was left to Charles Darwin after Hume's death. And how Hume would have relished the "I told you so" moment that Darwin would have handed him. The argument, the theological argument from design, or to design perhaps I should say, was familiar to Darwin because his cohort of Cambridge undergraduates was made to read William Paley. William Paley, the 18th century, early 19th century theologian, author of natural theology. His work, Natural Theology, was compulsory reading for Darwin's cohort of Cambridge undergraduates. Paley made the argument that if you're walking across a heath and you find a watch and you pick up this watch and you look at it and you open it and you look at the insides and you realise that it's clearly meant to be doing something, it's for a purpose, and perhaps you could work out what the purpose is. Its purpose is to tell the time. And Paley's argument was, well, the inference that this watch must have been designed applies a priori to something like an eye, which equally looks as though it's been designed, equally is performing some useful function, in this case not to tell the time, but to see. You could make this argument in a statistical way by pointing out that if you were to take the parts of a watch, or the parts of an eye, and scramble them around at random, and do it 1,000,000 times, 1,000,000,000 times, you would never once hit upon a scrambling of the parts which told the time, or which saw, or did anything useful at all. So the argument is a powerful one. Eyes, like watches, are statistically improbable, and statistically improbable in a specified direction, where that specified direction is in the direction of usefulness. You have to add that in a specified direction, because with hindsight, every random combination of rubbish, if you shake the parts of a watch or shake the parts of an eye into some random formation, every random formation that you hit upon will be unique, but it won't be unique in an interesting direction. And the interesting direction is the direction of functionality. It works, it does something useful. You could see why this, with hindsight, the improbability of some heap of rubbish is unconvincing. It's the classic one when you're playing golf and you drive the ball and it lands on a particular blade of grass, and you say, how fantastically improbable that the golf ball should land on this particular blade of grass. Not impressive at all. But if you hit a hole in one, if the ball goes right into the hole, that is extremely impressive, because the hole is specified in advance. Hitting upon an eye or a watch at random would be as impressive, perhaps even more impressive. So, random scrambling doesn't hit upon anything useful. The fact that a watch tells the time accurately in all sorts of complicated ways is impressive, and the same is true of eyes. You see here a variety of eyes. So everybody could see intuitively the force of the argument that if a watch is designed, an eye must be designed. But it's wrong. It's gloriously, definitely wrong. Human intuition is wrong. Hume spotted that, but didn't know what the alternative was. Darwin, as I say, spotted the alternative. The alternative to both chance and design. The alternative, Darwin's answer, is cumulative natural selection. Provided that a smoothly cumulative gradient of improvement exists from something very primitive, something very simple, something that doesn't work very well, say an eye that hardly sees anything at all, to a gradually improving ramp of eyes that see a little bit better than the one before, a little bit better than the one before, a little bit better, over 1,000 generations of improvement, say. Then you're going to get something highly statistically improbable, with an iris diaphragm that opens and closes to let in just the right amount of light, with a lens that can be focused, with a retina with millions of cells sensitive to colour, communicating with the brain. This comes about as a result of a cumulative series of improvements, where each one of those steps in improvement might have been random, actually was random, but was chosen non-randomly from the available alternatives by the non-random process of differential survival and reproduction. That is Darwin's seditious idea. It was seditious, it was revolutionary, deeply surprising. It eluded not only Hume, but every philosopher, every scientist, every mathematician, every great thinker before the 19th century. It waited to the 19th century, astonishingly, 200 years after Newton, whose achievement seems to us much more intellectually demanding. Nevertheless, it waited until 200 years after Newton, and then it came independently into the prepared minds of at least two 19th century English naturalists, Charles Darwin and Alfred Russel Wallace. Darwin and Wallace are not the only 19th century writers with some claim to priority for the idea of natural selection. I'm not talking about the idea of evolution itself, by the way. That's a much older idea. I'm talking about natural selection, the non-random survival of randomly varying hereditary information, as we would now call it. There is a claim on behalf of Patrick Matthew, a Scottish scientist who worked on trees, and Edward Blythe, 1810 to 1873. Edward Blythe, like Darwin, and I'll come on to Patrick Matthew in a moment. Edward Blythe, like Darwin and Wallace, was a naturalist in the tropics, a collector of specimens in the tropics, in his case India, in Darwin's case many parts of the world, mainly South America, and in Wallace's case South America and Southeast Asia. Blythe collected in India. He really did hit upon the idea of natural selection, publishing it in 1835, but his version of natural selection is the very limited form of natural selection which we would nowadays call stabilizing selection. Although he did in a way discover natural selection, thought of it as a stabilizing force, thought of it as actually stopping evolution happen. He was in fact a staunch creationist. He thought of natural selection as preserving God's original creations in their pristine, archetypal, unchanged state. He was the very opposite of an evolutionist. So natural selection in Blythe's formulation would amount to a force of resistance against evolutionary change. Patrick Matthew, whom I just mentioned, came much closer to the brilliant idea that Darwin and Wallace had. He had an orchard, a commercial orchard, where he grew apple and pear trees, and he was very interested in breeding trees. And he wrote a book called Naval Timber and Arboriculture. And in an appendix to this book, Matthew recognised the importance of artificial selection, which had long been known, the breeding of dogs, the breeding of cabbages, the breeding of trees, for human purposes. The non-random breeding, selection for breeding, but not natural selection. And Matthew was well acquainted with artificial selection, he practiced it, but then he recognised that it could be generalised to natural selection. You don't need to have a human to do the choosing. You can let survival do the choosing. So Matthew clearly got that point. Unlike Blythe, he did not see natural selection as a purely stabilising force. He went so far as to speculate that, quote, the progeny of the same parents under great differences of circumstance might in several generations even become distinct species incapable of co-reproduction. That's the definition of a distinct species, where you have sexual reproduction. Members of distinct species cannot reproduce in a fertile manner with each other. Well, when Darwin published The Origin of Species in 1859, Patrick Matthew protested at Darwin's failure to cite him, and Darwin punctiliously did so in later editions of the book. And Darwin acknowledged that Matthew, quote, this is quoting from Darwin now, clearly saw the full force of the principle of natural selection. And Matthew also clearly saw the importance of overproduction, another of Darwin's key points, and the consequent struggle for existence. Overproduction meaning that too many young animals and plants are born that can survive. Consequently, they compete with each other. Consequently, only the fittest survive. But having read Matthew, I'm left wondering whether he really did grasp the immense power of the discovery that he'd made. Did Patrick Matthew appreciate not just that natural selection would work, but that it is the answer to the great riddle of existence? Did he see it? Did he see natural selection as the explanation for all of life, as the destroyer of Paley's argument from design? If he had, if he'd really seen the importance of it, wouldn't he have published it in a more prominent place than the appendix to a manual on naval timber? Wouldn't he have trumpeted it from the rooftops as arguably the most important idea anyone had ever had? On the contrary, Matthew seems to have found the idea so obvious, almost trivial, as to need no discovery. In his complaint about being overlooked by Darwin, which he published in the Gardener's Chronicle, on the 12th of May, 1860, he wrote, "To me, the conception of this law of nature came intuitively as a self-evident fact, almost without an effort of concentrated thought. Mr. Darwin here seems to have more merit in the discovery than I have had. To me, it did not appear a discovery. He seems to have worked it out by inductive reason, slowly and with due caution, to have made his way synthetically from fact to fact onwards, while with me it was by a general glance at the scheme of nature that I estimated this select production of species as an a priori recognizable fact, an axiom requiring only to be pointed out, to be admitted by unprejudiced minds of sufficient grasp." Well, with hindsight, I think we can be tempted to sympathize with Matthew, but whereas T.H. Huxley, when he finished reading The Origin of Species, snapped it shut and movingly said, "How extremely stupid of me not to have thought of that." Matthew's response would seem to have been the Victorian equivalent of "big deal, so what else is new?" Is this the response of a man who 7 years before Darwin, 27 before Wallace, found himself in possession of the central unifying idea that dominates all biology and explains almost everything about life? I think it would be a fair, I'm now going to fantasize a bit, and imagine a 17th century ancestor of Patrick Matthew, a contemporary of Isaac Newton, watching an apple fall, perhaps in the very same orchard, for the Matthews had been farming in the Carse of Gowrie since the 16th century. Our earlier Matthew, our ancestral Matthew, I imagine to have been a physicist, as I say, and as he watched his apple fall, he conjectured that the earth exerted an attractive force on apples, pulling them towards it. If this hypothetical horticulturalist had later written to Isaac Newton and indignantly claimed priority for the theory of gravitation, Newton, who was a less generous man than Darwin, by the way, would rightly have given him short shrift. The physicist Matthew, I'm supposing, confined his theory to apples, or at best to objects falling towards the earth. He lacked Newton's grand vision of the same force acting throughout the universe, responsible for the elliptical orbits of the planets, for the stars in their courses, ultimately for the very structure of the universe itself. So I agree with Patrick Matthew's modern champion, W.J. Dempster, that Matthew has been unkindly treated by history. But unlike Dempster, I would hesitate to assign full priority to Matthew. I think it's partly because he wrote in a much more obscure style than either Darwin or Wallace, which makes it hard to know, in some places, what he was trying to say. And Darwin himself noted that. But mostly, I think he underestimated the importance of the idea, to such an extent that we now have to doubt whether he really understood quite how important it was. Alfred Russel Wallace was different. He discovered natural selection later than Patrick Matthew and later than Darwin, actually. But he has a genuine claim to be up there with Darwin and Newton among the immortals. When Wallace hit upon natural selection, he was in no doubt of its immense importance for the whole history of life. The very title of his paper, the one he famously sent to Darwin in 1858, which set the cat among Darwin's pigeons, says it all, on the tendency of varieties to depart indefinitely from the original type. Depart indefinitely, that was the key phrase. If they depart indefinitely from the original type, they can branch and branch and branch and eventually spawn all of life, beginning with something like bacteria. Wallace made this indefinite branching explicit in his paper. You probably know the drama of how Wallace's letter arrived at Darwin's house, on the 17th of June 1858, and it cast Darwin into an agony of indecision and worry. I think the whole episode is one of the more creditable and agreeable in the history of scientific priority disputes, because it wasn't a dispute, although it easily could have become one. It was resolved amicably, with heartwarming generosity on both sides. I think especially Wallace's. Wallace was a true gentleman. The 1858 paper of Wallace hit Darwin like a lightning bolt. The similarity between their thinking was uncanny. Wallace even used the phrase struggle for existence, the same phrase, and he devoted a great deal of attention to the exponential increase in numbers, which I've already mentioned as being an important Darwinian point. He wrote, "The greater or less fecundity of an animal is often considered to be one of the chief causes of its abundance or scarcity. But a consideration of the facts will show us that it really has little or nothing to do with the matter. Even the least prolific of animals would increase rapidly if unchecked, whereas it is evident that the animal population of the globe must be stationary or perhaps decreasing." So it doesn't matter how slowly, even elephants reproduce slowly. And Darwin did calculations with the help of his son George, to show that even with a slowly reproducing animal like an elephant, the rate of reproduction is pretty much irrelevant. It doesn't take very long for the world to become full of elephants, if nothing was there to reduce them. And of course, what's there to reduce them is competition with other elephants. As Wallace said, the numbers that die annually must be immense, and as the individual existence of each animal depends upon itself, those that die must be the weakest. And here is Wallace's peroration. "The powerful retractile talons of the falcon and the cat tribes have not been produced or increased by the volition of those animals, but among the different varieties which occurred in the earlier and less organized forms of these groups, those always survived longest which had the greatest facilities for seizing their prey. Neither did the giraffe acquire its long neck by desiring to reach the foliage of the more lofty shrubs and constantly stretching its neck for the purpose, but because any varieties which occurred among its antitypes with a longer neck than usual at once secured a fresh range of pasture over the same ground as their shorter neck companions, and on the first scarcity of food were thereby enabled to outlive them, and so on and so on. Historians have raised the suggestion that Wallace's version of natural selection was not quite the same as Darwin's, and they pointed out that Wallace persistently used the word variety as the level, the entity at which natural selection acts. And there was an example in the passage I just quoted. And he also used the word race in a similar sense. And some have suggested that Wallace, unlike Darwin, who clearly saw selection as choosing among individuals, not races, not populations, not groups, that Wallace might have been proposing what nearly all modern theorists now denigrate as group selection. And that would be true if, when Wallace used a word like variety or race, when he said that selection is choosing between varieties or races, he meant geographically separated groups of individuals, or races in the more usual sense of the word. But a careful reading of his paper rules that out. When Wallace talked about a variety or a race, what he meant was what we nowadays call a genetic type. What a modern population geneticist would mean by an allele. Local races, about varieties. He meant not a local race, for example, eagles, but that set of individual eagles whose talons were hereditarily sharper than usual. Nothing to do with a race. Those individual eagles that, genetically speaking, he didn't want to use the word genetically, we would now, inherited the quality of sharp talons were the ones who were likely to survive. And it's a similar misunderstanding that Darwin himself suffered, because he used the word race in the subtitle of The Origin of Species, preservation of favoured races in the struggle for life. Again, Darwin didn't mean races. Darwin meant something like what a modern geneticist would mean by an allele. As for the unfortunate calumny that Darwin plagiarized Wallace, that's rubbish. The evidence is very clear that Darwin thought of natural selection long before Wallace, though he didn't publish it. We have his abstract written in 1842, his longer essay of 1844. Both those establish his priority very clearly. Why Darwin delayed so long before publishing is one of the great mysteries in the history of science. Some historians have suggested he was afraid of the religious implications, others the political ones. Maybe he was afraid of upsetting his devout wife. Maybe he was just a perfectionist, keen to have all his evidence lined up in place before going public. Or he may just have got distracted by barnacles. He did spend a great deal of that period doing a meticulous study of the taxonomy of barnacles. When Wallace's letter arrived in 1858, Darwin was more surprised than we today, I think, believe he had any right to be. He should have thought, why didn't I mean, the idea is such a powerful idea, why didn't he publish it 10 years, 15 years earlier? He said, I never saw a more striking coincidence. If Wallace had had my manuscript sketch written out in 1842, he could not have made a better short abstract of it. Even his terms now stand as heads of my chapters. The coincidence between the two men extended to both of them being inspired by Robert Malthus on population. Darwin gives the account in his autobiography of how he was immediately struck on reading Malthus for amusement, as he said, on Malthus's emphasis on overpopulation and competition. He wrote, in October 1838, that is 15 months after I'd begun my systematic inquiry, I happened to read for amusement Malthus on population, and being well prepared to appreciate the struggle for existence which everywhere goes on from long continuous observations of the habits of animals and plants, it at once struck me that under these circumstances, favourable variations would tend to be preserved and unfavourable ones to be destroyed. The result of this would be the formation of new species. Here then I had at last got a theory by which to work. Wallace's epiphany after reading Malthus took longer to happen, was more dramatic when it came. It came to his overheated brain in the midst of a malarial fever on the island of Ternate in the Moluccas archipelago. I was suffering from a sharp attack of intermittent fever, and every day during the cold and succeeding hot fits had to lie down for several hours, during which time I had nothing to do but to think over any subjects then particularly interesting me. One day, something brought to my recollection Malthus's Principles of Population. I thought of his clear exposition of the positive checks to increase, disease, accidents, war, and famine, which keep down the population of savage races to so much lower an average than that of more civilized peoples. It then occurred to me, and Wallace proceeds to his own wonderfully clear exposition of natural selection as the guiding principle of all evolution. Now, I talked about 5 bridges, and I now want to go through my list of bridges more quickly. These are bridges to our understanding of natural selection. And I can illustrate the first 4 bridges by mentioning each of 4 people that I've already noted to you. Edward Blythe crossed the first of Darwin's 4 bridges, Patrick Matthew the first 2, Wallace the first 3, and Darwin all 4. So the first bridge is to natural selection as a force for weeding out the unfit. And I've already used Blythe as my example. The only reason to single him out is that he's been championed by Laura Isley as a predecessor, possibly even a possible source of Darwin's ideas. As Stephen Gould has argued, however, the idea of natural selection as a weeder out, purely negative force, didn't originate with Blythe. It was already widespread. And Gould even quotes William Paley himself as setting out this purely negative version of natural selection. And as I've remarked before, it's an anti-evolution argument. The second bridge is the recognition that natural selection can drive evolution in a positive direction towards different species. In modern jargon, it's the difference between stabilizing selection and directional selection. Matthew, Wallace, and Darwin all cross this second bridge. Bridge number 3 leads to the imaginative grasp of the importance of natural selection in explaining all of life in all its richness, and especially to dispel the illusion of design. Wallace and Darwin crossed it. I've already given reasons for thinking that Patrick Matthew possibly didn't. Bridge number 4 is the bridge to public understanding of the importance of the idea. Wallace understood the idea, but it was Darwin alone who crossed the 4th bridge. Crossed bridge number 4 in 1859 as opposed to 1858 by writing The Origin of Species. It is a striking fact, which Darwin himself remarked upon, that when the Darwin-Wallace joint papers were read in 1858 to the Linnaean Society, the resolution to the possible priority dispute was that Lyell and Hooker, 2 of Darwin's most trusted friends, suggested that what they should do would be to read Wallace's paper and 2 papers of Darwin, which he'd written much earlier, to the Linnaean Society in public so that the priority could be equal. That was the very gracious solution that was arrived at. But as Darwin remarked, when these papers were read out in 1858 to the Linnaean Society, nobody took a blind bit of notice, even the professional biologists of that august body, the Linnaean Society. The end-of-year clangor of the hapless president of the Linnaean Society, Thomas Bell, has become notorious. It will ring on down the ages. In his review, his presidential review of the Society's transactions in 1858, he said that the year 1858 had not been marked by any of those striking discoveries which at once revolutionized the Department of Science on which they bear. The end of 1859 would have to be reviewed very differently. The Origin of Species struck the Victorian solar plexus like a steel. The world of the mind would never be the same again, neither science nor anthropology, psychology, sociology, even, here we come to the dark side, politics. This book, The Origin of Species, which Darwin always described as the abstract of the great book that he intended to write but never completed, this book achieved what the 1858 papers did not. It's not just that The Origin of Species explained the idea more clearly, Actually, Darwin's and Wallace's papers of 1858 were very clear. The real difference, I think, was that a book-length treatment was required to muster all the evidence, lay it out for all to see. One long argument, as Darwin himself called it. And Darwin himself said, "This shows how necessary it is that any new view should be explained at considerable length in order to arouse public attention." Is there a fifth bridge which Darwin himself never crossed? Well, we are more than 150 years on now, and there are several. The one I want to single out today, but I'll mention some others in my subsequent lectures, is the bridge to so-called neo-Darwinism, the modern synthesis. Neo-Darwinism is a union of Darwinian evolution with Mendelian genetics. And I need to explain a little bit about what that means. I call it digital Darwinism. Before Gregor Mendel, the Austrian Czech monk who discovered modern genetics, it was thought that heredity was blending. Everybody knew that children inherited aspects of their father and their mother, but they vaguely thought that the paternal substance and the maternal substance were somehow blended together, somehow mixed together, rather like mixing red and blue paint. Now, if that were true, as was pointed out by a Scottish engineer called Fleming Jenkins, if that were true, and everybody thought it was true, then variation would disappear from the population. I talked about mixing red paint and blue paint. If you mix red paint and blue paint, you get purple paint. But then if you mix purple paint and purple paint, you never recover the original red and blue, you just get more purple. So if heredity were blending, like mixing substances, variation would vanish as the generations go by. There would be no variation for natural selection to work upon. Therefore, Darwin's theory must be wrong. And that was how Fleming Jenkins advanced the idea. It's obvious nonsense, because, of course, any fool can see that, as a matter of fact, variation doesn't disappear. Fleming Jenkins was objecting not to Darwin's theory, but to observed facts. However, Darwin was worried by it, and it gave him some grief. And it wasn't really solved until Mendel. Mendel was actually Darwin's contemporary, and he had published his brilliant work on peas, where he showed that inheritance is not blending, inheritance is digital. If you cross wrinkled peas and smooth peas, you get one or the other, you don't get an intermediate. And so heredity is digital. And if heredity is digital, then the entire Fleming-Jenkins problem vanishes. And that was realized not really until the 20th century. Although Mendel was Darwin's contemporary, alas, Darwin's German wasn't that good. And nobody brought it to his attention. Nobody else even realized how important Mendel's work was. It was rediscovered in the early 20th century, in 1900. And the full significance of it for Darwinism wasn't really realized until the great triumvirate of population geneticists in the 1930s. R.A. Fisher on the left, J.B.S. Haldane in the middle, and Sewell Wright on the right. Fisher, Haldane and Wright buried Fleming-Jenkins. Genes are digital. Genes are things you can count. Genes are things that have a frequency. There is a thing called a gene pool, which is a place where genes can be thought of as stirred about. At any particular time, of course, they sit in the bodies of individuals, but because of sexual reproduction, you can think of a population of animals or plants as a gene pool in which these digital entities, these countable entities, have a frequency. And that frequency can go up or it can go down. And if it goes up, then we have evolution in a positive direction. If it goes down, we have evolution in a negative direction. Natural selection is one way, the most interesting way, the most important way, in which the frequency of genes in a population can change. Those genes that are good at surviving are the ones that become more numerous in the gene pool. Bad at surviving genes become less numerous. What does being good at surviving mean? It means good at building bodies in which to survive and reproduce, giving bodies whatever it takes to survive for the species concerned. I've got this picture of Sewell Wright just because it's rather an interesting story. You see behind him mathematical formulae. All three of these gentlemen were very good mathematicians. Sewell Wright also did experimental work on guinea pigs. And the story goes that after this picture was taken, he absent-mindedly picked up the guinea pig and erased it. Even these three founding fathers didn't know quite how digital genetics actually is. In the light of the Watson-Crick molecular genetics revolution of the early 1950s and ever since, we now know that the very genes themselves is not just that each gene has a kind of all or none property. The very genes themselves are digitally coded information exactly like computer tape. The only difference is it's not binary but quaternary. Otherwise, it is a computer code. Modern genetics has become a branch of information technology. Of the three founding fathers, I think it was Fisher who most clearly, in his book of 1930, The Genetical Theory of Natural Selection, most clearly expressed the evolutionary significance of blending inheritance and its Mendelian digital antithesis. As Fisher showed mathematically, if genes did indeed blend, then the variation available for selection would be halved in each generation, just like the paint. Because of Mendelism, that doesn't happen. There's no inherent tendency for variation to disappear. If gene frequencies change, it's for interesting reasons, which the most interesting is natural selection. Fisher began his book by showing how close Darwin himself came to the idea of digital heredity. Fisher quotes Darwin as follows in a letter to Huxley. Darwin said, "I have lately been inclined to speculate very crudely and indistinctly that propagation by true fertilization will turn out to be a sort of mixture and not true fusion." He means not blending, not true fusion of two distinct individuals, or rather of innumerable individuals, as each parent has its parents and ancestors. I can understand on no other view the way in which crossed forms go back to so large an extent to ancestral forms. But all this, of course, is infinitely crude. So Darwin is looking, he sees as a kind of mixture where you're not just mixing mother and father, but there's a sort of mixture of grandparents and great-grandparents. He's kind of tentatively grasping the idea of Mendelian heredity in that passage in a letter to Huxley. But even Fisher didn't know how breathtakingly near Darwin really was to discovering Mendelian digital genetics. Darwin even worked on sweet peas, as Mendel did. In 1867, Darwin wrote a letter to Wallace that began as follows. "My dear Wallace, I do not think you understand what I mean by the non-blending of certain varieties. It does not refer to fertility. An instance will explain. I crossed the painted lady and purple sweet peas, which are very different coloured varieties, and got, even out of the same pod, both varieties perfect, but none intermediate. Something of this kind, I should think, must occur at first with your butterflies. Though these cases are in appearance so wonderful, I do not know that they are really more so than every female in the world producing distinct male and female offspring." Note that last sentence. It's a beautiful example of the power of reason, the importance of seeing straight through the obvious. When a male mates with a female, you don't get a hermaphrodite. You get either a male or a female with approximately equal probability. In a way, Mendel never needed to go into his monastery garden, never needed to work on sweet peas at all. All he had to do was take his armchair and think about sex. Take the inheritance of sex itself and generalize it to other cases of inheritance. Digital heredity was always staring us in the face in the most obvious way you could imagine. The trouble was, it was too obvious to be noticed. Darwin noticed it, and he came close to making the connection, but just as Patrick Matthew didn't quite cross the bridge that Darwin and Wallace crossed, bridge number 3, so Darwin didn't quite manage to cross the Mendel-Fisher bridge, at least not decisively enough to answer Fleming-Jenkin. Well, I distinguished bridge 1 from bridge 2 as stabilizing selection versus directional selection. There's more to it than that, though. Or perhaps the distinction I'm now about to make really separates bridge 2 from the Darwin-Wallace bridge 3. I want to talk about the distinction between selection as a negative force and selection as a positive constructive force that puts together complex new, quote, designs. And my preferred way of doing this, which is what we call the selfish gene way, is again to deploy digital genetics. So maybe we really need to cross bridge 5 in order to paint the full picture. In modern genetic terms, which is not Darwin's own, natural selection is the non-random survival of randomly varying coded instructions for how to survive. We admire the products, what biologists call the phenotypes, of the good genes. The instructions are DNA. Their most visible products are bodies that survive by doing something impressive, like flying or swimming or running or digging or climbing, hunting, grazing, all in the service of reproduction, which is ultimately what it's about, which means, of course, they also have to be good at attracting a mate, good at warding off rivals, good at parental care, and so on. Now, each gene in the gene pool is surviving in an environment. And you think of the environment as the environment of the phenotypes, the environment, the grassland, the woodland, the forest, the predators, the prey, the parasites. And that's, of course, the environment of the bodies in which genes sit. But an important part of the environment that each gene must exploit, if it's to survive, in the form of copies of itself, is the other genes that it encounters in the genomes of a succession of bodies. Remember that genes don't float around freely in a pool. They're all the time locked up in individual bodies, and they shuffle only when it comes to sexual reproduction. As a result of having to survive in the company of other genes in the gene pool, in the succession of bodies, cartels of mutually supportive genes cooperate to build bodies that specialize in some particular method of surviving, grazing or hunting or digging, whatever it is, as I said before. Different cartels are the gene pools of different species, and they're bound together within the species by the remarkable phenomenon of sexual reproduction, and they're separated from the gene pools of all other species. Occasionally, through accidents of geography, gene pools find themselves split in half, subdivided, perhaps a river runs between them, perhaps an earthquake separates them, perhaps there are islands offshore, and some individuals get blown off course by a high wind and land on an island where they find virgin territory that they can colonize. If that happens, then the gene pool is split in two, and the two halves of the gene pool are now free to go their separate evolutionary ways. They're no longer contaminating each other by sexual reproduction. They're free to go separately, and they go separately, possibly because of different natural selection pressures on the island or the mainland, or possibly just by sheer chance. But as a result, eventually, they become so separate from each other, genetically speaking, that they can no longer interbreed in the event that they happen to meet each other. They have become separate species. Successive branchings in this way have given rise to all the diversity in the whole of life, billions of separate species. Every 2 species you care to name, a common ancestor, literally an individual, most recent common ancestor, which lived maybe nearly 1 billion years ago. A single individual had 2 children, one of which was destined to give rise to us, the other of which was destined to give rise to snails. And when I say us, I mean all vertebrates, all sea urchins, starfish, sea squirts on the one hand. When I say snails, I mean plus insects and crustaceans and many worms and so on. Every pair of species you care to name are cousins of each other who can trace their ancestry back to a single common ancestor. An ancestral gene pool split, possibly by the sort of geographical separation that I mentioned. And once they split enough that they were no longer interbreed, they were on their own for the rest of time. And they diverged and diverged and diverged further, evolved and evolved further, until they ended up as different as humans from snails. At least in sexually reproducing species, evolution consists of changes in frequencies of genes in gene pools. Now I have to stipulate sexual reproduction because without it, we have no really clear idea what a gene pool even means. A gene pool doesn't mean anything unless there's some mechanism for stirring the genes, which is what sexual reproduction does. But where there is sexual reproduction, the gene pool is the set of available alleles, available genes, from which the individual members of a species draw their genomes, draw as in a lottery, draw as in getting dealt a hand of cards. Each individual genome is like a shuffled pack, a shuffled subset of cards from a great big pack, which is the gene pool. The statistical frequencies of these available cards in the gene pool change as the generations go by. That is evolution. We monitor evolution by measuring the phenotypes, the anatomy, the physiology of typical members of the population. As the average phenotype changes, as legs get shorter or horns get longer or coats get shaggier, whatever happens to be evolving at the time, it's tempting to see natural selection as a sculptor's chisel carving the bones, the flesh of the animals themselves. But if you want to talk about chisels, a sharper representation of evolution would see the chisels as working not on the bodies of animals, but on the gene pool, on the statistical structure of the gene pool. As crests get longer, or eyes get rounder, or tails get gaudier, what's really being carved by the chisels of natural selection is the gene pool. Mutation, that's the random changes in genes, and sexual recombination enrich the gene pool with more variety, and then the chisels of natural selection carve the gene pool into shape by the mechanism of killing off some animals and allowing others to live, or favouring the reproduction of some animals. So we observe the results in the form of changes in the average phenotype, the average shape, size, behaviour, etc. of the animals. Phenotypes can be thought of as proxies for genes. And as the external and visible manifestation of genes, they determine whether or not the genes survive or are eliminated. Because if a body dies, all the genes in it die. So the survival of the genes depends upon the survival of the vehicle, the body, successive vehicles, successive bodies in which it resides. The species gene pool is a database which becomes a storehouse of information about the environments of the past, environments in which ancestors survived and passed on the genes that helped them to do so. To the extent that present and future environments resemble those of the past, and they usually do, the world doesn't change in a capricious way, to that extent, this, what I call genetic book of the dead, will turn out to be a useful manual for survival in the present and future. The database has been carved by the chisels of natural selection in the past. It therefore can be regarded as a database of information about the environments of the past. To the extent that the environments of the past are a reliable guide to the environments of the future, then individuals possessing those genes will survive, and that is another way of putting natural selection. Each individual's genome in any one generation will be a sample from the species database. Different species have different databases because of their different ancestral worlds. Carnivores, herbivores, tree climbers, etc. have different databases. They've lived in different ancestral worlds. Like sand bluffs carved into fantastic shapes by the desert winds, the database in the gene pool of camels will encode information about deserts and how to survive in them. The DNA in mole gene pools will contain instructions and hints for survival in dark, moist soil. The DNA in predator gene pools will increasingly contain information about prey animals, their evasive tricks, how to outsmart them. The DNA in prey gene pools will come to contain information about predators, how to dodge and outrun them. The DNA in all gene pools contains information about parasites and how to resist their invasions. So natural selection carves and whittles gene pools into shape, working away through hundreds of millions of years of geological